In this video, I'm talking about important property of exponential form of complex number. In the last video, we have learned the so-called Euler's formula, e to the I theta equals to cosine theta plus sine theta. This clearly shows a way of converting between exponential form of complex number into modulus argument form of complex number and vice versa. Also, at the end section of last video, we talk about the complex conjugate of the complex number expressed in exponential form. The complex number z equals to r times e to the I theta. Okay, so I need to emphasize something here. Theta is measured in radian, and it is also a real parameter. Same with r. R is the modulus, so by definition, it is the absolute value of the complex number, or if expressed in a graph, it is the radius of the circle, and is represented by r. If it is the absolute value of a complex number, that means it is bigger than 0 and it is real. So let's return to the topic of complex conjugate. If we complex conjugate z, and we have done this part, we know how to complex conjugate this, but if you complex conjugate a real number, it does nothing because it complex conjugate only works for complex number, so it leave r intact. This we have seen before is e to the negative I theta. Now, in previous videos, we have talked about the important property when you times a complex number by its complex conjugate. We learned that it is real and positive. Now let's do it using the exponential form of complex number, which is r e to the I theta, e to the I theta plus times r e to the minus I theta. For e to the I theta and e to the minus I theta, I should write correctly, equals to e to the I theta minus I theta, which is 0, and e to the 0 is 1, so that's 1. We cannot leave r to r here, so there's r squared. If you cannot realize the significance of this, I should write it as the absolute value of z squared. So the absolute value of z is a real number and it is positive. So the square of a positive number would be positive, and the square of a real number would be real. And that's how we in using the exponential form, it's extremely easy to prove this relationship, and rather than using the Cartesian form. Now, if you have realized that we actually done a multiplication of complex number, that's the point that I'll explain next. This is only a special case, but in general it follows the same pattern. So for example, I have a complex number z and a complex number x. And complex number z, I use the same letters before, r times e to the I theta. And x, let's say big R times e to the I phi. Now, if we multiply them, we can see this is real and positive. This is also real and positive, and they go together. So it's r times big R and e to the I theta times e to the I phi. which is e to the I theta plus phi. So as you see, if you multiply two complex numbers, you multiply the modulus and add the argument. This only takes you about 1 second, but when you do the Cartesian form, like write a plus bi times c plus di, and I think it takes you more than 1 second. But when you actually performing other more complicated multiplication, using exponential form would be a shortcut. The division also has a similar pattern. This is r e to the I theta, big R e to the minus I theta, also e to the I high phi. This is r over big R e to the I theta minus phi. So when doing multiplication, you divide the modulus while you subtract the argument. Now let's return to the relationship that we stated before when we are doing the complex conjugate. Say if you complex conjugate a product of complex number, you will get this the product of complex conjugate of each complex number. And we leave it as an exercise when using Cartesian form of complex number, but since we learn the exponential form, we have done xz, so I don't have to write again. E to the I plus theta plus phi. And if you complex conjugate it, it does nothing to the real modulus, but it makes this negative. Put the negative sign here. And what we do is that we try to expand this e to the I theta times e to the I minus I phi. So maybe you realize some pattern here. So r times e to the I minus I theta, it is x, the complex conjugate of x, while big R times e to the minus I phi is complex conjugate of z. So the same pattern observed if you divide the two complex number, x over z complex conjugated equals to complex conjugate of x divided by complex conjugate of z. Next, I shall state a special case of the Euler's identity. Also, the Euler's formula, and this will lead to Euler's identity. So from e to the I, if we convert the exponential form into a modulus and argument form, if we is e to the I theta, but what if we put e to the I pi? Because we like pi, and we see if what happens. It equals to cosine pi plus I sin pi. So if you realize sin pi is 0, so the imaginary part we cross our imaginary part, while this leaves -1. This is extremely simple and elegant. It contains the three most understandable number, e, I, and pi, which this is a irrational number, and imaginary number. So Benjamin Peirce once quoted said, we could not understand what it is, but we prove it, so we know it is the truth.